Hello friends, in this video lecture we are going to discuss the Newton-Raphson method for load flow studies. First we will discuss considering all the buses as PQ bus in the part 1. So let us begin. We have discussed the things regarding the load flow study. We do have the idea what is the load flow study. Of course, we have discussed one of the important method to solve the load flow study. It was Gauss-Seidel method. We have seen Gauss-Seidel method in detail. So now in this video lecture, we are going to discuss the Newton-Raphson method to solve the load flow study. First, we will try to understand what is the Newton-Raphson method first. Then we will apply the things to solve the load flow problem. Okay. See, everything in this world has got certain constraint. It has got certain advantages, and of course, it has got certain disadvantages. So, first discuss the advantages of the Newton-Raphson method. See, Newton-Raphson method, it is one of the iteration method, or it is one of the numerical method to solve the nonlinear equations. Of course, you might have studied this Newton-Raphson method in your mathematics subjects. It is talking about the Newton-Raphson method advantages. It is the most powerful method for solving nonlinear algebraic equation. See, I must underline here the nonlinear algebraic equation terms. See, uh, to solve the load flow problem, we have nonlinear equations. The equations, SLFE equations, okay, static load flow equations that we have, those are the nonlinear equations. And of course, for each bus, we got two nonlinear equation. If we are going to solve for 100 bus, if suppose the power system is having 100 bus, we need to solve this nonlinear algebraic equation for almost say two equations for each bus, and we are having let's say 100 bus, then we need to solve this nonlinear algebraic equation for 200 times. So it becomes very difficult. So that is why we need an iterative method, or we need this numerical method. So the things is that the first advantage is that it is most powerful method. Okay, let that order of the nonlinear equation be anything. Okay, let us suppose that the nonlinear equations are having very n number of variables, then also it is a very powerful method. Okay, this is the first advantage. Second one, of course, when we are going for the iteration method, we expect the method to be a fast one, or what we expect, the method should converge rapidly towards the solution. So what method we are already knowing is Gauss-Seidel method. So let me tell you, friends, Newton-Raphson method is faster than Gauss-Seidel method. Okay, and the convergence is sure in most cases. Okay, see, of course, the convergence, it depends upon the initial assumptions from where we have started the iteration method. Okay, the thing was, in Gauss-Seidel method, the Gauss-Seidel method, it was very sensitive to the initial assumptions, but it is not the case in Newton-Raphson method. Okay, it is not that much sensitive to the initial assumptions. Okay, that is why it is said that convergence sure in most of the cases, as it is not relying on the initial assumption. So these are the certain advantages of the Newton-Raphson method. Of course, as I said, everything comes with certain plus and certain minus. So Newton-Raphson method, the disadvantage is that it requires memory storage requirement is more. This problem, this disadvantage, it was the issue in earlier days when we were not having the computers that we have these days. These days we have computers with enough memory. Okay, so these days this memory requirement is no more disadvantage, what we can say, because we do have developed our computers which are having, or which offer lot of memories for us. Okay, so disadvantage, we can say it was a early days disadvantage. These days we have overcome this advantage because we have enough memory with us. Okay, so let us now understand what exactly we have to do in the Newton-Raphson method. Okay, initially assume that we have n nonlinear algebraic equations. Okay, and of course, those n nonlinear algebraic equations will be having n number of variables. Okay, see, these variables, these nonlinear algebraic equations, let these equations will be f of I, and it is a function of this n number of variables. Okay, for I is equal to 1 to n, as it is said that n nonlinear algebraic equations are there. Okay, see, it is the case. We can relate this with our load flow problem. We have got algebraic equation in terms of active power and a reactive power. Okay, of course, these are the functions of uh, phase angle and voltages. Okay, I hope you remember those static load flow equations. From that, you can easily relate that these equations are the functions of phase angles and the voltages. Okay, so I can relate this equation, this nonlinear algebraic equation, with the static load flow equations that we have. Okay, so suppose initially consider that a set of nonlinear algebraic equations is given by this equation. Okay, now what is the task? We have to find out these variables. What are the variables? This x1, this x2, this x3 up to xn. These are the variables. We have to solve this nonlinear algebraic equation to get these variables. Is it the case? See, if it is a PQ bus, then P and Q will be specified to us, and the unknowns are phase angle and the voltages. Okay, this is what we find for the PQ bus. Okay, so what we have to do, each iteration or each numerical method, it start with assumption. So same is the case we have to do in Newton-Raphson method. We have to start with some assumption. So let us assume that those variables that we have been using in this nonlinear algebraic equations, let us assume some values for them. Let us assume some values for them. See, in Gauss-Seidel method, we have seen that uh, we started the that iteration sometime with the flat start, where we have taken the voltage as 1 and the phase angle as 0, or the voltage magnitude in terms of rectangular form as 1 plus j0. It was a flat voltage start. Okay, this we have seen. The initial value, how to guess this, we have seen this. So same is the case in Newton-Raphson method. You have to start with some initial value. Okay, suppose these variables are having initial value. See this 0, this power 0 indicating it is an assumed value, or these are the initial values. Okay, so let this is the vector which is having these variables x1 naught, x2 naught, x3 naught up to xn naught. See this power not indicating these are the assumed initial values. Okay, and now suppose to this unknowns, to this initial assumed value, if I add certain correction, on adding certain correction, if I'm getting the exact variable, suppose the variable, exact variable for, let's say for example, if I say x1 is having exact value as 4.5. This just for example I'm giving you. Suppose this is the exact value of x1. If I'm going with this iteration method, suppose if initially we assumed that x1 naught is 4. Okay, so definitely if I add something to this value, that would give me the exact solution. So that would be the correction in this. That would be the adding certain correction to this. Suppose if I add certain correction, let's say 0.5, and that correction would be small value of this x1. So this will give me the exact solution. So this is what given here. if this del x1 naught, del x2 naught, del x3 naught, suppose these are the corrections to be find out. Okay, we have to find out this correction in such a way that if I add this correction in the respective unknowns, then that will give me the actual solution. It will give me the actual solution. See, that is what it is given here. Corrections to be find out, and after adding these corrections, then that corrections or that variable will give me the exact solution. Now I have the exact value for the variables x1. Okay, same is the case up to xn. Okay, so this is what we have to do in Newton-Raphson method. What is the main thing we have to do? Initially, you can assume anything. Okay, you can go with the flat voltage start. Okay, the main task here is to find out the correction. Okay, finding the correction is the main task, because assumption is not a big deal. You can assume any value, but the correction is very important. Okay, see, I don't know what is exactly value of x1. Here just I have given the example. Okay, if you assume the value as 4, then you have to find out this correction, that is 0.5. So this finding this correction is very important. Okay, because ultimately if you get the correction, then only you will get the unknown, then only you will get to know the value of this x1. Okay, so what same is the case. Let us relate this thing with our the exact load flow problem. Suppose if it is a PQ bus, what are the unknown? This voltage angle and the voltage magnitude. These are the unknowns. Suppose initially we assume some value for this phase angle and the voltage. So after getting this, we have to find out the correction in this assumed value. The correction to be added to the assumed value, so that we should get the exact voltage and we should get the exact phase angle. Okay, this is what we have to do in Newton-Raphson method. But it is not that easy to get the correction. To get the correction, we have to take the help of a Taylor's series. Okay, so whatever equation now, actual solution we have here, see, I'm going to expand this actual solution by using Taylor's series. Okay, so let us see how we can expand this actual solution with the help of Taylor series. Function f of I 0, it indicates the function is being calculated with the initial values or the assumed values. See, even in the bracket also it is mentioned this x1 not indicating it is a initially assumed value. Xn naught up to xn naught 50. Okay, plus now we have to take the partial differentiation of the function with respect to each variable. Let us take the partial differentiation of this function with respect to each variable. We are having n variable, so n number of terms n number of terms will come here. Partial differentiation of this function fi with respect to x1. Of course, that x is equal to the initial assumed value multiplied with the correction in that variable. Okay, now take the partial differentiation of the function with respect to x2. Of course, the x, these are the assumed value. Okay, multiplied with the correction in the x2. This way you have to go up to xn, plus certain higher order terms will come in this Taylor series, and of course it is equal to 0. Okay, so we have expanded this equation or this actual solution. Why we are expanding? Because I'm interested to find these corrections. Okay, so n number of corrections will be there. We need to find out those corrections, because when we get the correction, we will add that correction to the initial assumed value, and that will give us the actual solution. So to find out the solution, we are doing all these things now. Okay, so firstly, what we did, we have taken the help of Taylor series to expand this solution, to expand this function. Okay, now let us ignore this higher order term. Okay, let us ignore this higher order term. Okay, if I neglect this higher order term, then this equation number 3, that is the Taylor series expansion, it can be written in the matrix form as, see here, it is function in the assumed value or in the initial values. So I can write it here as, let us suppose this is the first equation with initial assumed value. Second equation, we have n number of nonlinear algebraic equations. So up to fn plus, here we have to take the partial differentiation of f of I is mentioned. So first we'll start with I is equal to 1, because we have to go from for all values of I, we have to consider it. Inverse A indicate all values. So I will start from 1 to n. Okay. So this way, f of f of 1 divided by differentiation of this first function with respect to x1, differentiation of this first function with respect to x2, dot 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 up to differentiation of this first function with respect to xn. Okay, of course these are the initial assumed values. Okay, next, differentiation of this second function with respect to x1, differentiation of second function with respect to x2. This way you have to get this. Okay, see, this is nothing but what we are doing, we are writing this equation in terms of matrix form, that's it. Okay, this way you have to go up to differentiation of function fn, nth function with respect to first. First we have to take the partial differentiation of nth function with x1, x2. This way we have to continue up to xn. Okay, of course we can write, see these are in multiplication, so we can write it in a separate column matrix as del x1 naught, del x2 naught up to del xn naught. Let us equate it to 0, because it is equating it to 0. So let us call this as equation number 3. Okay, next, broadly or in general or in short, I'm going to write this as, I'm writing this as, see these this is consisting of functions in initial assumed variables. So f naught indicating a function in initial assumed variable plus this matrix, this whole matrix. See, it is a Jacobian matrix. See, since it is a consisting of a first order partial differentiation. Okay, as it consists of a partial differentiation, first order partial differentiation, so it is a Jacobian matrix. If it consists of second order partial differentiation, it will become a Hessian matrix. Okay, that is the term related to the matrices. We are not going in detail to that types of the matrix, but as it is a this matrix is consisting of partial differentiation, so it is called as Jacobian matrix. So for Jacobian matrix, I'm using the term J into this column matrix, or this is the correction vector matrix. So del x1, del x2, these are the correction vectors, is equal to 0. Okay, so this is equation number 4. What I'm doing here, I'm just rewriting this equation as f naught is equal to, if I shift that term, of course it will become a negative sign, j naught del x naught. Okay, see this power 0 is indicating these are being calculated on initial assumed variables. Okay, or initial assumptions, on that initial assumption they are calculated at the initial assumptions. Okay, now see, now we know the functions are known to us. Okay, what is to be find out, I'm interested to find out these corrections. So for this we already know the functions. How we know the functions? See, function f naught, let me write the f naught here. Suppose f of I naught I'm writing, for sake, let us say f1 of naught. Definitely it will have the variables like x1 naught, x2 naught, x3 naught up to xn naught. So as we have assumed some values for these variables which are nothing but x1 naught, x2 naught, definitely this will have some numerical value. So if I put this numerical value, I'll get some value for this function. So that is what I'm telling you. I know this f naught now. Okay, with the help of this f naught, we can evaluate this Jacobian matrix. Okay, we can evaluate this Jacobian matrix. Okay, if we get this F naught and J naught, we can calculate this correction vector or the correction in the variable, okay, or the correction in the quantity which is to be find out. Okay, so let us furthermore rearrange this equation number 5. Now I'm putting this correction to be which is to be found out on this side. If I shift this Jacobian matrix on the other side, it will become inverse of the Jacobian into F naught. Okay, once you get this correction, what you have to do, you have to add this correction into the initial assumed value. That will give you a modified value. It is giving you a modified value. Okay, so after getting the modified value, you have to check for the convergence criteria. Okay, if with this modified value, if the functions or if equations are converging, then we can stop. If it is not converging, then we can go for next iteration. Okay, so in general, let's say for rth iteration, and for the rth iteration, this x of r indicating value of x in rth iteration. How we can get this? Of course, we can take the reference of this value of x in the previous iteration plus the correction in that variable in the previous iteration. Okay, how we have evaluated this correction in the previous iteration? Of course, we have evaluated with the help of this equation. For that, refer this equation number 6. Minus j naught, x naught was there, j naught, so x of r minus 1 will be Jacobian matrix which was evaluated at variables in r minus 1th iteration. Okay, and a function which was evaluated in the variables in r minus 1th iteration. Okay, so with this you will get the correction, and after getting the correction you have to find the modified value. Once you get the modified value, check for convergence. Okay, so now the question arises, for how many iterations we have to continue this? You have to continue this process until this convergence criteria is satisfied. What is the convergence criteria? See here, iterations are continued till, suppose this is the tolerance. What is the tolerance? Suppose this is tolerance. What is the tolerance? You have to take the maximum of this value. See, this is the first function in x which is being calculated in rth iteration, second function in rth iteration, third function in rth iteration. Likewise, you have to go up to nth function in rth iteration. You have to find out, or you have to evaluate each function value, okay, in each iteration. Okay, after finding out this function value, you have to find for which function is giving maximum value. Let us suppose that in this case f2 is giving the maximum value. You take now f2 here and you check whether that f2 is, whether it is less than or equal to the specified value or not. If it is less than or equal to specified value, then you can stop your iteration. If suppose if it is greater than the specified value, then you have to go for next iteration. Okay, now what is the specified value? Now it depends, the specified value, it depends on the nature of the study. Suppose if you are going for the rigorous study, we keep this tolerance, or we keep this specified value as low as possible. See, it can be either 10 to the power minus 9, or it can be set, in some cases we consider that tolerance as 10 to the power minus 12 as well, if it is a very rigorous study we are carrying out. If suppose if it is just a future planning purpose, if you are doing that, then in that case you don't need a rigorous or exact values. Then in that case you can set this tolerance as some higher values, let's say 10 to the power minus 3 or 10 to the power minus 6. It depends, the specified value or that tolerance value, it depends on the nature of study for which purpose we are carrying out the study. Okay, now is it understood now? So we have to continue the iteration till this condition is satisfied. Okay, Let us suppose that in rth iteration, this condition is being satisfied. What is the condition? The condition is tolerance must be less than or equal to the specified value. If it is the case, suppose if it is the case in rth iteration, so whatever variable values we got in rth iteration, that will be the solution. That will be the solution. Okay. Now I hope the things are clear to you. If suppose if you didn't get this condition satisfied in the rth iteration, you have to go for one more iteration, or you have to go for some more iterations. How you will go in the rth iteration? You have to find the correction in the variable x. Okay, because of course we have this xr with us. Okay, we have to find the correction in rth iteration. Okay, add this with the x which is with us in the rth iteration. This will give us the value of x in r plus 1th iteration. It means that for next iteration we'll get the variables now. Okay, so we have to check for this convergence criteria in r plus 1th iteration. If it is satisfying there, then this will be the solution. If suppose if furthermore if it is not satisfied, then what you have to do? You have to find out correction. Finding out correction, it can be done with the help of this equation. Okay, so find out the correction in r plus 1th iteration. You have x in r plus 1th iteration. That will give you the x in r plus 2nd iteration. So in this r plus 2 iteration, check for convergence criteria, satisfied, stop it, not go for next iteration. So this way you have to continue for Newton-Raphson method. Okay, it's very lengthy method, but it is a very powerful method. Of course, it is a faster one also. Okay, so let us apply the understanding of Newton-Raphson method for the load flow study. Okay, see, I'm dividing this into two parts. We are discussing the first part only now. Now, let us apply this Newton-Raphson method for load flow studies. See, why I'm dividing it in two parts. In the first part, I'm considering that all the buses are PQ buses. I'm assuming that all the buses are PQ buses. Suppose there are n number of buses are there. Of course, what we do, the first bus we always take it as a slack bus. So the bus number 1 will be a slack bus, and rest of the first bus, how many buses will be left with us? From bus number 2 to bus number n. Assume that all these buses as PQ bus. Okay, so this would be the case 1 for us, where we are assuming that all the buses are PQ bus except slack bus. Okay, in the part 2 we'll consider the PV buses as well. Okay, first try to understand for PQ bus. If you understand this, we can apply the same understanding for the system which is having PV buses. Okay, so these equation, the equation number 1 and 2, these are the SLFE, static load flow equation. We have already discussed these equations. We have derived these equations from the complex formula. Okay, pi summation k going from 1 to n yik vk cos of theta ik plus del k minus del I. Okay, this is for real power and this is for reactive power. Okay, be sure here it is having a negative sign here. Okay, okay, so we have already seen why this negative sign is coming here. See now, suppose now I'm going to define some function. Let this is fi function. What is this fi? It is a change in the real power. Delta indicating change, pi is the real power. Okay, I indicating on ith bus. Okay, what will be that change? It is scheduled power on the ith bus minus actual power in the ith bus. Okay, see what happens when we do the unit commitment. In that case, what we do, we commit or we schedule certain real power on the buses, okay, on the generator. Okay, and sometimes the actual power It's not exactly the same as the scheduled power. Okay, so if it is the case, so in that case, so certain difference will be there. Okay, this is the scheduled power and this is the actual power available on the ith bus. So this will give me the difference in the real power. Okay, same for the reactive power. The difference in the reactive power, scheduled reactive power minus actual reactive power. Okay, now you please try to understand one point here. These scheduled values are the constant values. These are the, because once we decide the scheduling, then that will become a constant value. Means this real power, suppose on the let's say for on the second bus, if it is decided that the real power, if it is scheduled that real power, it would be, let's say if it has decided to be 100 megawatt. On the reactive power, it was decided as 50 MVAR. Okay, it is a reactive power. If it is decided, so easily you can see here, these are the constants. So these two are the constant. But what about the actual power? I can say that it is the function of the phase angle and the voltage available on the ith bus. The power on the real power on the ith bus and the reactive power on the ith bus, it is depending on the phase angle and the voltage, both this real and reactive power. Okay, so in this function, I can say the first term are constant and the second terms, these are the function equations of in the unknowns as del, the phase angle and the voltage. Okay, now if you remember in Newton-Raphson method, just now we have discussed this equation we have discussed. Okay, to get the correction vector, we have seen this relation. Okay, function in the earlier iteration is equal to minus Jacobian inverse, and that Jacobian is evaluated and the r minus 1th iteration or the preceding iteration into correction in the variable in the, of course, in the same iteration, r minus 1th iteration. Okay, if with this for ith PQ bus, okay, because first one is the slack bus, leave that bus. Next buses from second to n, we have all the buses as PQ bus. That is what we have assumed in the beginning. Suppose on any bus, let's say for ith bus, of course it will be a PQ bus. So on this bus, I can write it as this change in PI, and change in QI, it is equal to, see now here, I'm applying the same thing. This is my function f of r minus 1. It means that function in preceding iteration. So function is change in pi, change in qi is equal to negative sign. Negative sign I'm writing here. Okay, Jacobian matrix evaluated in the same iteration. So of course we have to take the inverse of this. Okay, and this is correction in the variables. Okay, corrections in the unknowns. Specifically, unknowns will use this term. Okay, so before we proceed, now you tell me if it is a PQ bus, what we know about the PQ bus, P and Q are specified. What is unknown? Phase angle and voltage. These are unknowns. These are to be found out. This is the idea we know regarding the PQ bus. Okay, so now let us try to understand how to write this Jacobian matrix. Function, we have to take the partial differentiation of the function with respect to unknowns, with respect to the variables. So variables here are phase angle on the second bus, phase angle on the third bus. So corrections we have to deal with. Correction in the phase angle on the second bus, correction on the third bus, correction this way in the phase angle on the nth bus. This is the correction for the first variable, that is the phase angle. On each bus, on different buses means PQ bus, start from second number bus, go to n number bus. Take the partial differentiation of this Pi with respect to the second unknown. What is the second unknown now? Voltage on the same bus. Phase angle and voltage, these two are the unknown on the same bus. Okay, that's why again we have to continue this. Take the partial differentiation of this active power with respect to V2, V3, this way go up to Vn. What about the second function? It is Qi, or the change in Qi. Okay, same way you have to take the partial differentiation with all the unknowns. Okay, now let us decide the order of this Jacobian matrix, or the order of the all the matrix. Here order is simply, it is 2 by 1 matrix. Here the order is, see, two rows we can see. So 2 by, how many columns are coming? So first is, we are going from 2 to n. Again, this was for phase angles and this is for voltages. We are going from second to nth bus. Bus n minus 1 buses will become, or n minus 1 terms will come. See, totally what I can say, let me give the idea here. From 2 to n we are going. We are going from 2 to n we are going. It means that we are dropping the first bus. So we can say for phase angle, totally I'm taking n minus 1 terms. Is it? And for voltages, we are taking n minus 1 term. Because we are not taking all n terms. We are dropping the first term. Why? Because on the first bus, that is the slack bus, we do the calculation at the end. Okay, because we always handle the things related to slack bus in the end only. So we'll drop that bus. So the terms left with us will be n minus 1 for the phase angles and n minus 1 for the voltages. So this way columns would come as 2 times n minus 1. So the order of this Jacobian matrix is coming to be 2 by 2 times n minus 1. Now what about this unknown vector order? It would be, see how many rows will come, 2 to n. It means that n minus 1 and again 2 to n, again n minus 1. So 2 times n minus 1 by a single column is coming. So by 1. Okay, so this is the ordering of this matrices. Okay, now let us try to know the each term which I have written in this matrices. What is delta Pi or delta Qi? Okay, so for this, let me make it further more simple. Let us make it further more simple. Delta P, change in the P or the difference in the P. How we can find it out? Scheduled value minus actual value. Scheduled reactive power minus actual reactive power. It is equal to. Now this is Jacobian matrix. Okay. Now let's say these are the elements of the Jacobian matrix: J11, J12, J21, J22. Okay. And these are the corrections. The correction in the phase angle and the correction in the voltage. Okay. Now what is this delta P or change in P? It is actually a vector of change in real power on each bus. Bus range starting from second to n. So order would be n minus 1 by 1. Change in Q, it is again same. Second bus up to nth bus. Change in delta or the change in the phase angle. It is, of course, it is also change in del 2, change in del 3. This way you have to go up to change in del n. Change in V, you have to go the same thing. Change in voltage at second bus, change in voltage at third bus, go up to change in voltage at nth bus. So these how these terms are. Now we know how to calculate this difference. Means I know now how to calculate or how to get this difference in real power and reactive power. It is quite simple. You have to take just the difference, scheduled power and actual power. Okay, of course, again this matrix, this vector, we have to find for, because we are finding for the correction. So now we should know how to get this Jacobian matrix or how to evaluate this Jacobian matrix. That is very important. Okay. Now let us try to understand how to evaluate the Jacobian matrix. Once we understand this, then this method of Newton-Raphson method, it becomes very simple for us. Okay, so let us go and discuss one by one each terms of Jacobian matrix. See now, first I'm writing it for J11. Now I'm writing it for the first entry in the Jacobian matrix, that is J11. Of course, it is a matrix. J11 itself, it is a matrix. J12, it is also a matrix. J21, it is again a one matrix. J22, it is, of course, it is again a one separate matrix. We'll deal with that. We'll deal with all these four elements of Jacobian matrix one by one. First, we are beginning with J11, first element. See, 1 indicating you have to take the first element from this side, first element from this side. So it would be the partial differentiation of the real power with respect to the phase angle. Partial differentiation of the real power with respect to the phase angle. Okay, now you may be getting one question here. You see here it was a minus sign, it was there. Now I'm not taking a negative sign here. I'm dropping that minus sign. Why? Because that explanation is given here. You just see here this P, actually J11, if you see J11, it is nothing but partial differentiation of this change in P with respect to change in phase angle. Okay, see, that is what I have written here. Partial differentiation of this change in P, particularly on ith bus with respect to phase angle on the jth bus. Okay, see now, partial differentiation with respect to phase angle at jth bus. What is change in Pi? It is nothing but just now we have discussed power at ith bus, scheduled power at ith bus minus actual power on ith bus. Okay, just now I told you that this scheduled value is a constant value. The differentiation of this constant will become 0. Now we get this term. Okay, so now this is negative, so this negative will come here. So what we are getting here, partial differentiation of the power, real power on ith bus with respect to phase angle on jth bus. Okay, so we are getting this negative term, negative sign. So that negative thus minus minus get cancelled. That is why I have not considered the minus sign in the second step. Okay, so see now, I can write this broadly in matrix form as J11. It is nothing but partial differentiation of real power on ith bus, okay, with respect to the phase angle on each bus. Okay, we'll see that. See, first let us assume that it is a second bus. So partial differentiation of the real power on the second bus with respect to the phase angle on the second bus. Same thing, partial differentiation of the real power on the second bus with respect to the phase angle on the third bus. This way you have to go up to partial differentiation of the real power on the second bus with respect to phase angle on the nth bus. Next row, partial differentiation of the real power on third bus with respect to the phase angle on second bus, third bus, nth bus. This way you have to go up to nth bus. So J11 is a matrix which is having n minus 1 by n minus 1 terms. Okay. Similarly, J12. See now, J12. First term from this side, second term from this side. It will be partial differentiation of this change in P with respect to change in voltage. Okay, let's see that. J12. If you solve this, you'll get the matrix this way only. See, if you can do this, you'll get the same matrix as partial differentiation of P2 with respect to B2, partial differentiation of P2 with respect to B3. This way you will get n minus 1 by n minus 1 order matrix. Okay. Now J21, it will be second term from this side and first term from this side. It will be partial differentiation of change in Q with respect to change in phase angle. J21, partial differentiation of Q reactive power with respect to phase angle. Okay, what is change in Qi? It is scheduled reactive power on ith bus minus actual reactive power on ith bus. Okay, the scheduled value is a 0. So we are getting partial differentiation of qi, that is reactive power on the ith bus with respect to the phase angle. You see here, what is change in qi or what is change in reactive power? It is scheduled reactive power minus actual reactive power on ith bus. The scheduled reactive power, it is actually a constant value. The constant variable, the differentiation of the constant is nothing but 0. So we'll get this minus partial differentiation of qi with respect to phase angle. So again, we are getting a negative. That is why the minus sign, once I have taken the common, and the minus sign which was there outside the Jacobian matrix, it is now getting cancelled. Okay, so this way you can write J21, which is nothing but the partial differentiation of the reactive power on the second bus with respect to phase angle on the second bus, partial differentiation of the reactive power on the second bus with respect to the phase angle on the third bus. This way you can write. Okay, so you'll get n minus 1 by n minus 1 terms for J21. Same, we can do for J22. You can do this. Just we have to take the partial differentiation of the reactive power with respect to the voltage. It is quite simple, but it is a bit lengthy because you have to write each time n minus 1 by n minus 1. That is why this was the disadvantage for the Newton-Raphson method, because it is taking so many, so big matrices we are getting. Suppose if it is 1,000 bus system, so you can imagine 999 by 999 matrix. So you can imagine the memory requirement. These days it is not the issue. Early days where we were having systems where hardly RAM was 256 MB or 500 MB. In those days it was the issue. But these days we have the supercomputers where even a normal computer or the laptops that we carry, it is now coming with a RAM of 8 GB or more than 8 GB. Okay, so now this is not the big issue. Memory, we can take any order of the system. Okay, and we'll get the results as quickly as well. Okay, now the J11 term we have discussed here, how to get this in the matrix form. Okay, now I want to know, I want to get a generalized terms or a generalized equation for this. See now, you just concentrate here. These terms, these are the diagonal terms. Okay, these are the diagonal terms in the J11, and rest of the terms are off diagonal element. See what is the difference between diagonal terms and the off diagonal terms. Here, the real power I'm taking on the second bus, the phase angle will be on the second bus only. Real power on the second bus, phase angle on the second bus, real power on the third bus, real power on the phase angle on the third bus, real power, partial differentiation of the real power on nth bus with respect to the phase angle on the nth bus. So these are the diagonal element, and rest of them are off diagonal element, where the partial differentiation on the bus 2 we are taking with respect to phase angle on bus 3, or the partial differentiation of bus 2 we are taking with respect to phase angle on the bus n. So these are the off diagonal elements. So let us see, let us have a general form or the general equation to get this term J11, or to get this element of the Jacobian matrix. How we can get that? Let us see that. Let us discuss that. Yeah, I've done this here. J11. See what is J11? So you have to be now. You have to be with this matrix in your mind. What is the matrix? Let me write that matrix here. P Q J11, J1, J21, J2. These are change in angle and change in voltage. You have to be this relationship is it should be with your in your mind now. J11, first term, real power, phase angle. Okay. Now partial differentiation of the real power on ith bus with respect to partial differentiation with respect to phase angle on jth bus. Specifically, I'm taking it as I is not equal to j. It means that I'm dealing for non-diagonal non-diagonal elements. I'm dealing with this term here. Okay. Of course, we'll see how to get the diagonal element as well. Okay. So when these terms are not same, it will give us the non-diagonal element. When this becomes same, it will give us the diagonal element. Just now I have given you that thing. Okay. So Pi. Now take that static load flow equations. From that Pi, it can be written as Pi summation k going from 1 to n yik bk cos of theta ik plus del k minus del I. Okay. See now, let me expand this summation. I'm keeping this Vi as common. First term, yi, let's say k is equal to 1. yi1 v1 cos of theta I1 plus this k is 1 del 1 minus del I. Okay, this way when k is equal to 2. Okay, now one more term I want to write here. I'll write that term here because that will give you the simple idea. Now suppose let me write the jth term where k is equal to j. Now I want to write that term I j bj cos of theta ij plus del j minus del I plus continues. Now the last term, nth term, where k is equal to n. Yin Vn cos of theta in plus del n minus del I. Okay, so this way this terms continues. Now you see here we are taking the partial differentiation with respect to which term? We are taking it with respect to this del j. Now you see in this equation, in this term, where you are finding the del j. I'm finding that del j here. Okay, is there anywhere you are finding del j? No. So rest of all the terms will become 0. Only we have to take the differentiation of this. How we can take the differentiation of this? You see, Vi, it is a common, keep this Vi outside. See now, cosine, this del j is inside the cosine. So you have to take the differentiation of this cosine. The derivative of cos is minus sign. Okay, so see here, minus I'm writing here, yijvj is constant, yijvj constant. Derivative of cos, it is now becoming sine of theta ij plus del j minus del I. Okay, so in short or in general, can I write this as j11? See this, when I is not equal to j, it indicates this is off diagonal terms. So we can evaluate the off diagonal terms with the help of this equation now. What is the equation we have now? Minus Vi yij bj sine of theta ij minus del j minus del I. See, these terms will be given to us. Okay, or else what I can say, see, if it is a PQ bus, P and Q it is known. What we are doing, we are assuming some value of voltage and phase angle. So this assumed value we can put here and we can get the value of this J11. We can get the value of this J11 of diagonal term. We have to take the respectively I, J, we have to take care of this terms. Okay, so J11 terms related to J11 you can get by with the help of this equation. Now these are non-diagonal elements. Now when I is equal to j, it will give me the diagonal element. So let's see how to get the diagonal element. See now, j11 partial differentiation of real power I with respect to the phase angle on the same bus, on ith bus. It is now del partial differentiation of this bracket with respect to phase angle on ith bus. See now that pi equation, I'm expanding it in this way. Let's say b I am keeping it out. The summation I'm expanding by I1. Let's say k is equal to 1. Bk, it will become as k is equal to 1, it will become b1 cos of theta I1 plus del 1 minus del I plus. Let me write the ith term. Second, third, fourth, somewhere ith term will come. Phi I vi cos of theta I plus del I minus del I plus goes up to nth term. Okay. Now you see here this del I minus del I plus del I minus del I will get cancelled. Okay. Again, we are taking differentiation with respect to del I. Okay. Are we taking this? Yes, we are taking differentiation of with respect to del I. Now you have to take care where we are finding or where do we have this del I term. On each term we have this del I. If you concentrate, if you see, if you imagine, you can see, or if you write all the term, you will find that in each term we have this del I. Okay, again, it is having a negative sign. So if I take derivative of cos, it is becoming minus sign. And furthermore, we have to take the derivative of this angle as well. So minus del I. So that minus, this minus getting cancelled. So what we are getting here, you see here, what we are getting here. See, let me give the idea to you now first. If suppose cos of minus theta is given, okay, and you have to take the differentiation of cos of minus theta with respect to theta. It becomes, how do we write? First we write derivative of cos theta. It is sine theta, we write as it is, minus theta. And then what we do, we take the differentiation of this angle with respect to this theta. So if I take differentiation of this, with minus will come here. If I take derivative of this, so I'll get minus 1. So minus minus it become sine of minus theta. Okay, this is how, this is the understanding you have to apply here. Okay, so cos derivative is minus, but this my angle derivative is again minus, so that minus minus getting cancelled. Vi, keep this term outside. V y I1 V1, this term is cos is becoming sine theta I1 plus del I del 1 plus del I plus, see this term uh, plus so on. This is ith term. This is for ith term. We are not having any del I on in the ith term, so this derivative is becoming 0. Now in the nth term, again we get yin Vn sine of theta in plus del n minus del I. Okay, so how we can write this? Can I write this as summation form? I want to write this. So just see here, I'm writing Vi. Let me write this Vi as it is outside. Summation. Let's say k is equal to 1 to n. Now I'm specifically mentioning here k not equal to I because ith term has become 0 now. So what I'm getting here, yi1. Next term will be yi2, yi3. So can I write this as yik, v1, v2 up to vn. So can I write vk, sine of theta I1, theta I2, theta in. So can I write theta ik, del 1, del 2 up to del n. Can I write del k minus del I, it is same. So let's keep this del I as it is. Okay. Now what I'm going to make some changes here. Now let us see what changes we can have here. That ith term is missing here now. So what I'm doing here, I'm adding that ith term and I'm subtracting that ith term. So try to understand this. If I add ith term here, so this k not equal to I condition is going. Now as I'm adding that term, I must subtract the same term. What is that term? Where I is equal to, where k is equal to I. So yi sine of theta I plus del I minus del I. Okay. So adding and subtracting. So add and subtract, you'll get this term. Now you see here this term, v into this term. Is it equal to qi? Is it equal to qi or minus qi? Yes, if you refer the static load flow equation, it is equal to minus qi. Now, this plus del I minus del I get cancelled. So what we will left with here, yi, this vi, if it comes in bracket vi square, it makes sine theta ii. Okay, see this yii, can I write this as yii as yii to the angle theta ii? If I write this in a rectangular form, y cos theta, y sin theta. Y cos theta is the conductance, it is the admittance. We write this as conductance plus susceptance. So yii into sin theta ii is nothing but the susceptance value. So I'm replacing this yii into sin theta ii with susceptance bii. Okay, so this is how we can get the diagonal term of the J11. It's the diagonal term for J11. Okay, so we have seen the off diagonal element for the J11. Now we have seen how to calculate the diagonal term of the J11. Same way we have to evaluate it, the each term of the Jacobian matrix. Now I have done here the same way for J12. It is nothing but first term on that side, second term on that side. Partial differentiation of the real power with respect to voltage. Now you have to do the same thing. First you do it for off diagonal term, then you do it for diagonal term. Okay. Pi, if you write that Pi and you expand it and you differentiate it with respect to Bj. Okay. See here here we are getting the term Bj. Rest of all term is not having Bj, so all those will become zero. Only you have to take the derivative of this. If I take the derivative of this, Pi, it will come inside Pi into Yij cos of theta ij plus del j minus del I you will left. Okay, do the same thing for the diagonal terms of J12. Okay, try to do it on yourself. If you do this, you'll get this equation. Okay, now you can do this respective correction. Let us do this. Rest I'll give you directly the value. You can evaluate that and you can reach counter check it. For the diagonal element, partial differentiation of real power and I bus with respect to voltage on the same bus. So keep this Pi in common. Expand this Pi summation yi1 b1 cos of theta i1 plus del 1 minus del I. Okay, plus so on up to ith term yii bi cos of this angle goes up to nth term. Okay, now you see here everywhere vi, it is being getting multiplied everywhere. Okay, vi will get multiplied here, vi will get multiplied with second term, with third term, the ith term or up to nth term. When it is being getting multiplied with the first term, see rest of all the terms are constant. It is a partial differentiation, only vi is the variable. So what are the remaining is the coefficient of the vi. We can as it is copy that coefficient vi1 b1 cos of theta i1 plus del 1 minus del I plus up to. See now, this pi when it gets here, it becomes pi square. Rest of the terms are nothing but coefficient for vi. So vi square derivative will be 2vi into yii cos. You see here, this del I plus del I minus del I get cancelled. So it is here we are getting cos of theta ii plus same goes up to nth term. Okay, now you see here, let us write this in general. Let's say summation k going from 1 to n. See yi1 b1, that terms we can write this in this way yik bk, okay, cos of theta ik plus del k minus del I plus this term yii bi into cos of theta ii. See how I have written here in this term, in this summation specifically, I must write here k not equal to 1. Okay, so that compensation I have done here, where I'm adding and subtracting that k not equal to 1, and I'm on solving this, you'll get this term. Okay, if you solve this, you please check. This is nothing but pi divided by vi. Vi is missing here now. If I add one vi, it will become pi. But since vi is missing, so we can write it as pi divided by vi plus this vi. You keep this as it is. Pi I into cos of theta I. It is becoming conductance. So this is how you can calculate the diagonal terms for the J12. Okay. Now it is now quite simple or easy for you to evaluate the remaining term J21 or J2. Okay. You can try this and you can verify this with these values I have written here. Okay. If you find any correction, please let me know. Okay. Now get back to this master key. Get back to this equation. Correction in P, correction in Q is equal to Jacobian matrix is equal to correction in the unknowns. Okay, now what you have to do is, first whatever assumptions you have made, based on those assumptions, first you calculate change in P and change in. This is the first case you have to do. Second, what you have to do next, evaluate Jacobian matrix. Okay, once you get this, you can easily get the correction in the unknowns. See, as it is a PQ bus, the phase angle and the voltages, these are the unknowns. Okay, once you get this, you will get the change in phase angle and correction in the voltage. Once you get this, modify the phase angle in R plus 1 equation and the voltage in R plus 1 equation. Once you get this, again go back to the same thing. Evaluate change in power, change in reactive power, evaluate Jacobian matrix, get the get the corrections in the unknowns, okay, and modify the value. This way you have to continue. Okay, you have to continue up to the convergence criteria is satisfied. Okay, again, of course, I have given you how to set the convergence criteria. It depends on the nature of the study that we are carrying. Okay, so this is how we can do if the power system is having PQ buses. Okay, so we'll stop for part 1. In the next part, we'll deal with the power system which is having PV bus as well. Thank you very much.